This time, Year 10, we're going to look at neutralisation and pH. So to begin with, as a little starter to warm us up, please can you complete the following in your exercise book. Please pause the video and have a go at these word equations, and we'll go through the answers shortly. So hopefully you can see, Year 10, that when you react hydrochloric acid, HCl, with copper carbonate, CuCO3, you form a salt, in this case copper chloride, CuCl2, water and carbon dioxide. So this is the general equation for this is acid plus a metal carbonate makes a salt, water and carbon dioxide. In the case of the balanced symbol equation here, because you form copper chloride CuCl2, you need to have two hydrochloric acids to get the equation to balance. Underneath that, sulfuric acid, again that's an acid reacting with copper carbonate and metal carbonate, forming copper sulfate as the salt, water and carbon dioxide. It's already balanced, you can see the balanced symbol equation here. In the third example, it's exactly the same as the first one, except that you've got magnesium carbonate instead of copper carbonate, which means that you're going to form magnesium chloride rather than copper chloride, MgCl2. And again, you need to have two hydrochloric acids because the formula for magnesium chloride is MgCl2. The last one is very much like the second one, except you've got magnesium carbonate again rather than copper carbonate. So it's sulfuric acid plus magnesium carbonate makes magnesium sulfate, water and carbon dioxide. And provided you've used the correct formulae, and there was some little hint on the slide, it should be relatively straightforward to get the right balanced equation. Well done if you got all of those right. So as I've mentioned, we're looking at C5.7 today. Neutralisation and the pH scale, or just neutralisation and pH for short. You can find information on this in the AQA digital textbook on pages 96 to 97, or you can search neutralisation on the BBC Bite-Size website. Next little thing to think about then, Year 10, are these equations here. Which are the acids in each equation, which are the bases in each equation, which are the salts, and as a bit of extension, have a go at writing the balanced symbol equations for the above. I've given you some hints underneath here yet again as to the formula for the relevant species in each equation. Pause the video now and give this a little go. Well done, Year 10, for giving this a go. The answers are here on screen. So hydrochloric acid is an acid. So sulfuric acid, as the name implies, and nitric acid as well. So I've colour-coded these. The ones in red are all the acids, and I've included the formula underneath in terms of the balanced symbol equations. You'll see in a moment why I've colour-coded them in red. The bases are colour-coded in purple. Sodium hydroxide, calcium hydroxide, potassium oxide. Bases are substances that neutralise acids. And again, the formula are written underneath each word equation so you can see the formula of each base. Now, the top two, as we've described before, just to remind you, the top two are a special type of base. They're called alkalis because they dissolve in water to form hydroxide ions. The salts are in green: sodium chloride, calcium sulfate, potassium nitrate, and the formula are written underneath. Well done if you got those all right. The first one is very straightforward, it's already balanced. The second one already is balanced, but remember that the 2 here means that there are 2 hydroxide ions in this substance here. And the last one is the most difficult to balance. You need 2 nitric acids because you've got 2 potassiums to form 2 potassium nitrates, and water, of course. All of these reactions are neutralisation reactions. That is to say, if you've got a molar ratio equivalent to each other, so 1 mole of this, 1 mole of this, you'll form 1 mole of calcium sulfate and 2 moles of water in this case. If you've got precisely the right number of moles of each to neutralise each other, the pH will end up as being 7. Neither acidic nor alkaline. In the end, you form water, as we will see. Today, Year 10, we're looking at neutralisation and pH. Hopefully you've already written a title in your exercise book. We're going to go through to the laboratory in a moment to have a go at a little experiment. Before you do, just visualise the pH scale for me in your head. Hopefully what you should have is some sort of rainbow. Richard of York gave battle in vain, going from red through to violet or dark purple. Let's go through to the lab though and let's do an experiment. So I've got a beaker here which is full of water. We can tell it's water because I'm going to put in some universal indicator, and you'll see that when I put in the universal indicator it goes green, showing that it's pH of 7. I'm going to turn on a little magnetic stirrer here. So this device here is a magnetic stirrer. There's a magnet in the base here that spins, and it causes the magnet in the bottom of the beaker here to also spin, just so that I don't need to stir the solution. And if I rotate it a little bit, you'll see that in the middle there's a little vortex forming as it spins the solution, which is rather good. Wait for that to mix in. And next I'm going to take some hydrochloric acid. I'm going to add some drops of hydrochloric acid and we'll see what happens to the colour of the solution. So I'm adding in a few drops and straight away it's changed colour, just a few drops. It's gone orange, pH probably 4, something like that. And I'm going to keep going. Keep adding a few little dropwise and you'll see that the solution has gone red. It's become a pH of about 1. Just a relatively small number of drops and already the colour's changed quite dramatically. Next step, I'm going to take some sodium hydroxide. I'm going to slowly add this to it dropwise and we'll see what happens. In the middle, you might notice where the mixing isn't great, there's a purple column forming, but let's keep adding more sodium hydroxide. And as it mixes, we might notice that it's going to change colour. It's slightly less red than it was before. It's becoming more and more orange as it mixes in. It's just on the cusp of changing, so let's leave it to mix in. A little bit more. Starting to change colour, slowly going yellow, pretty impressive, and then back to that original green colour that we had, pH 7, and then through to blue, and eventually all the way through to purple. We've now got a strong alkali. But we can go back the way we came. We can take some more hydrochloric acid. This is a reversible reaction, and I can add more hydrochloric acid to the solution so that we get back to where we started from. So beautiful colour change, back to green, back to yellow, and then all the way back to red, showing that now we've got a strong acid. So we saw in real time there the pH scale being starting at pH 7, going down to pH 1, and then all the way up to pH 14 and back down to 1 again, as part of a little demonstration involving strong acids and strong bases. Strong acids have a low pH, right? All acids have a pH lower than 7. If something is at pH 7, it's neutral. So strong acids have a low pH. Weak acids have a relatively high pH, i.e. more than 1 but lower than 7. So this region here is where you will find a weak acid. Conversely, strong alkalis or strong bases have a very high pH, much higher than 7. All bases, all alkalis have a pH higher than 7, but strong alkalis have a pH that's very high, 13 or 14, and weak alkalis have a pH of about between 8 and 10. I'd like you to copy out this diagram, please, into your exercise book. Can you also label it with just what we've talked about? If you need to rewind the video prior to this point to be able to do that, please do so. But I'd like you to label up where are the strong acids, where are the weak acids, where is neutral, where are the weak alkalis, and where are the strong alkalis. And we'll go through the answer in just a moment. Please pause the video to do that now. Hopefully this is what you've put onto your diagram, something along these lines, where at low pH you've got a strong acid. The closer you get to 7, the more it becomes like a weak acid. Bang on 7 is neutral, and the opposite is true for alkalis or bases. So pH 14 is a strong alkali, and the closer you get to 7, the weaker the alkali it is. So between pH 1 and 6.9, we say it is acidic. pH 8 to 14, we say is alkaline or basic. Here's a nice little illustration of the pH scale, showing various different substances, items that you'll be intimately familiar with, and where they lie on the pH scale. So gastric acid, that is to say acid in your stomach, hydrochloric acid is pH 1, lemon juice, apple juice, tomato juice, black coffee, milk are all acidic. Pure water is neutral. Eggs are slightly basic. Baking soda, hand soap, ammonia, bleach are all basic or all alkaline. So now that we've done that, let's flip over to a new sheet of paper and write down the pH of a strong acid, a strong alkali, a weak alkali, a weak acid, a weak alkali, and a neutral solution. What colours would each occur, right, under universal indicator? And why is it difficult to use if you want a very precise pH? What could you use instead? So pause the video, have a go at writing down the pHs, the colours, and answering this question here of why is it difficult to use universal indicator if you want a precise pH. Pause the video, we'll go through the answers in just a moment. Okay, Year 10. Hopefully you got the following. That a strong acid has a pH of 1, it's red. A strong alkali has a pH of 14, it's purple. A weak acid has a pH of about 6, it's yellow, but you could really have anything from sort of 4 to 6 here. A weak alkali has a pH of 8 and it's blue, again about 8 to 10 is acceptable. A neutral solution would give you a pH of 7, which is green. The reason why universal indicator isn't used if you want specific pH values is that the colours are subjective. Green, well, there's lots and lots of shades of green. So if I want a neutral solution of exactly pH 7, I can tell that it is some value of pH 7 if the solution is green, but there are lots and lots of shades of green. It's very difficult to say definitively whether it's pH 7.00. So a pH meter is used instead, which is where you have a pH probe that measures the conductivity of the solution, and the higher the conductivity, the conductivity will change depending upon the pH. And the meter will interpret the conductivity read by the probe and will give you a specific reading, usually to 2 decimal places on the meter here. So a pH meter is used to give specific pH values, usually to 2 decimal places, which is much more accurate. It's much closer to the true value. So really what we need to think about is what makes an acid and what makes an alkali an alkali. These are 2 very difficult questions, and are questions that chemists have wrangled with for a very, very long time. However, I'd like to think about it a little bit. If it helps to think about examples of acids by flicking back through your exercise book, and the same for examples of alkalis to help you to answer each of these questions, please do. Pause the video now, make some notes in your exercise book, and we'll go through the answers when you're ready. An acid dissolves in water to release hydrogen ions. So whenever we think about an acid, we say that it contains hydrogen ions. Well done if that's what you wrote down, that it contains hydrogen. Hydrochloric acid is an example, HCl, but you might have written down H2SO4 for sulfuric acid or HNO3 for nitric acid. Hydrochloric acid, HCl, when it dissolves in water, forms hydrogen ions and chloride ions. And these hydrogen ions here are what give rise to acidity. Pretty much all acids release hydrogen ions when you dissolve them in water. For an alkali then, an alkali dissolves in water to form hydroxide ions. For example, a very common alkali is sodium hydroxide. Sodium hydroxide is a solid. When you dissolve it in water, yes, it forms sodium ions, but that's not important. This could be any metal. It could be potassium hydroxide or lithium hydroxide, but it forms hydroxide ions. That's the key thing. Those hydroxide ions are what make alkalis alkalis. So when an alkali dissolves in water, it releases hydroxide ions. Please pause the video if you need to update your notes for the fact that acids release hydrogen ions when dissolved in water and alkalis release hydroxide ions when dissolved in water. So if you think about the pH scale, when you have a pH of 7, that means that you have an equal number of hydrogen ions and hydroxide ions. H plus OH minus makes H2O. So it's neutral. There's no overall charge. There are no hydrogen ions, there are no hydroxide ions. It's in perfect balance. There's no net charge. As you go further this way, down the pH scale here to pH 1, low pH means that you've got a high concentration of hydrogen ions. Conversely, at high pH, that means you've got lots of hydroxide ions. Because alkalis release hydroxide ions, that means that you've got a high pH. So just to confirm, pH 7 is neutral. It's neither got a high concentration of hydrogen ions or a high concentration of hydroxide ions. It's balanced. You've got pure water at pH 7. The lower the pH, the higher the concentration of hydrogen ions. There's lots of H plus at low pH. At high pH, conversely, there's lots of hydroxide ions. It's the flip side of the coin. Please pause the video and update your notes as ever. So to finish with Year 10, I'd like you to copy out this triangle and fill in your experiences from the lesson today. What have you seen? What have you done? What have you thought? And what have you learned? And in terms of that centre part of the triangle, what have you learned? What are the real key things that you've learned today? Pause the video, have a go at this, and I'll hopefully give you a little recap at the very, very end so you can see what we've covered today. Okay, in summary today, Year 10, hopefully you've learned that acids produce hydrogen ions when they dissolve in water. Bases are substances that neutralise acids. Again, that's something that we should have learned in previous lessons, but nevertheless it's something worth reminding ourselves about today. Alkalis are a special type of base which are soluble in water and they produce hydroxide ions when they dissolve. You've also seen about the pH scale, which is used to measure the acidity or alkalinity of a solution. Solutions with a pH greater than 7 are alkalis, less than 7 are acids, and pHs of exactly 7 are neutral. Thank you as ever for your attention, Year 10. I'll set a little quiz on this through Teams so you can judge your learning, and have a very fantastic Easter when we get there. Well done.